Okay, we're continuing our discussion of the particle in a box, interpreting the results. And in this video, I'll talk about the particle in a box energies. This is the equation for the particle in a box energies. Again, you get this from solving the Schrodinger equation. And what's interesting is you get the introduction of this quantum number n imposed by the boundary condition that the wave function go to 0 at the edges of the box. Just like with the wave functions, when you derive an equation for the energies of a quantum system, you should draw an energy level diagram. And here's what that would look like. I'm going to make an axis. That was supposed to be straight, but oh well. Energy is going up this way. The lowest energy level will be 0. And then you start to plug in this number n. Now, what you'll see is that the energy depends on the square of n. And so what it will make sense to do here is to plot energy in h squared over 8ml squared units. Right? You can show that that's an energy unit, and we'll think about it in those energy units. And so I start plugging in values of n. Right? The lowest number for n, particle box, is 1. If n is equal to 1, you have 1 energy unit. Second is 2. If n equals 2, you get 4 energy units. N equals 3, you get 9 energy units, etc., etc., etc. Right? This is an energy level diagram for a particle in a box. And now let me point out some things to you about this. The first is that the energy levels are quantized. Again, if this was a classical system, the particle would just ping back and forth. If I wanted to give it a little bit more energy, I just heat it up a little bit and it'd go a little faster. I cannot do that here. Only specific values of energy are allowed. It's quantized. This is the wave nature of the particle. It has to go to 0, so I can only get certain wavelengths in the box. Right? The energy levels are quantized. The second is perhaps even weirder, which is that the lowest energy level is not 0. Right? Look at this. If I took a classical system and I brought it to absolute 0, it would stand still. If this was a quantum mechanical system and I brought it to absolute 0, it would still have some energy. Right? And so this lowest energy is given a name which is called 0-point energy. Right? So even if I freeze this thing out, it's still wiggling at some level. And again, that's because of the wave nature of the particles and the uncertainty principle. Right? It's someplace in this box. There's an uncertainty in its position. Therefore, there's a finite uncertainty in its momentum, and it wiggles back and forth. Okay. 2 more important points about energy. You don't need that. I just told you that the energy levels of electrons inside of molecules are quantized, right? Given by this formula here. We also know from Einstein that the energy contained inside of light is quantized. It only takes on certain values. This is Einstein's equation, E equals h nu. What happens when these two match? Well, as you know from every chemistry course you've ever taken, if a photon comes in, it can promote an electron from the HOMO, this highest energy state, to the LUMO, the lowest energy state, where the energy of the photon matches this energy difference. Quantum mechanics, this is given a specific name. It's called the Bohr resonance condition. And it says a photon is absorbed when its energy matches the energy difference between levels. And I want to emphasize to you that this is not the absolute energy, but the difference between energy levels. So delta E is equal to h nu. We can use this to solve important problems. I'm not going to go through it in this video. It's on the worksheet. You should go through and do it. But it will turn out that the particle in a box model is a reasonable model for the electronic energy states of electrons in conjugated pi systems. So here's an example. This is a cyanide dye called Psi3. And it turns out that the energy levels arise from this conjugated pi backbone right here. So if I assume that this had a length of 1.1 nanometers, calculate the wavelength of light that is absorbed by the HOMO-LUMO transition. You can do this type of thing. Do it on the worksheet. Here's an equally important question. This molecule is called Psi3 because it has 1, 2, 3 carbons in its backbone. This one is called Psi5 because there are 1, 2, 3, 4, 5. Somehow my video just died. Okay, Psi5, 5 carbons in the backbone. Would the absorption of Psi5 occur at a shorter or a longer wavelength than Psi3, or the same? Right? Why? And what I want to point out to you is that there are really two things going on. The first is that the number of electrons is increasing. So we have more pi electrons in here. But more importantly, the backbone is extending. Right? The length of the box is bigger. And remember that energy is proportional to 1 over L squared. So if that box is increasing in size, its energy levels are going to shrink. And this is Psi3, right? The red one right here. Psi5, the teal one, I think it's this one here. Right. And this is perhaps one of the most critical things that we get from the particle in a box model. If you're a note-taking person, put this in your notes and circle it. As the box gets bigger, the separation between energy levels decreases. This is true in almost every quantum mechanical system. As you weaken the confinement, as it spreads out, as the box gets bigger, its energy levels shrink. And so here's another XKCD comic. I'll read it. It's my hobby, sitting down with grad students and timing how long it takes them to figure out that I'm not actually an expert in their field. In engineering, you got about less than a minute. Our big problem is heat dissipation. And the person says, have you tried logarithms? In linguistics, you get a little bit longer. So does this Finno-Ugric family include, say, Klingon? In sociology, now you're at tens of minutes. Yes, my latest work is on ranking people from best to worst. And in literary criticism, 8 papers and 2 books and no one's caught on yet. You see, the deconstruction is inextricable from not only the text, but also the self. Here's the point in quantum mechanics. You could reasonably begin analyzing any quantum mechanical question by saying, well, if we think of this as a particle in a box, okay, this is the starting point. The lessons from here are really important. As the box gets bigger, right, energy separation decreases. We have quantized energy levels with wave character. Okay, I'll stop here and we'll move on to some other permutations of the particle in a box problem.